Hello. So this is going to be a series of lectures linear on linear time varying systems. So what do I mean by linear time varying systems? So um, it is a system which is given by x dot equals atx, where x is a vector, is an vector with which you can write it in Rn. So x is something like this: x1, x2, xn, right? And A is a matrix which is whose entries are dependent on time. So A is in Rn by n, say, and the entries are dependent on time. So one example of which would be, say, let's take a 2D system. So x is x1, x2, right? And let's say the A matrix is something like 0, 1, cosine t, 0, x1, x2. So this particular one here, you see that it is periodic in time. So it repeats at a period of 2 pi. It is 2 pi periodic, right? So in this particular case, so our goal would be at the end of this, towards the end of this series of lectures, is to understand systems like this, right? But for now, we will be focusing on a much simpler system, because that's how we will start building the whole framework and move towards from the system, which is the first thing is the would be the scalar system, which is simply the 1D system. Then we'll look at a system with constant coefficient. So there would be no time dependence, like in the coefficient, there would not be any such time dependence. It will be a constant matrix. And then we will look into we will consider the system with more generality, where with a generic time dependence. And then we will specialize to periodic systems, so that we will look into where we can use something called the Floquet theory, because our end goal is to understand time periodic systems and to apply Floquet theory. So for a start, let's see the 1D linear. So all these systems are linear systems. So 1D linear time, sorry, time varying system, right? These are often called LTV systems, right? So as I said, I'll just consider a scalar equation: x dot equals ATX. And the question is, let's say that this is equation 1 with an initial condition x at time t equals 0 is, say, x0. And the question is whether we can solve this system, right? So yes, we can solve this system. And the solution of this is, I mean, I'm just going to write it. I'm just trying to show the integration here. It's dx by x is basically a t dt, right? And you integrate. So I'll just use a dummy variable here. You integrate from x0 to x, and time being integrated from 0 to t. So which means that your x is going to be, let's not write x, to be more specific, to be clearer, let's write it as x of t as x0 exponential of 0 to t a t prime dt prime. So this equation is a very important equation here, because this is the solution to the system 1. Okay, and so let me put a box around here. Okay, call it equation 2, right? So let's call this guy here this guy here. Okay, we'll call it as phi t. And what is phi t? It is known as the fundamental matrix. Now you can say that, okay, in this situation it is a scalar for sure. In this situation this is a scalar, but uh, you'll see that this kind of a format will be repeated every time. Okay, and there's and it's most easily understandable in this 1D system, right? So let's try to take an example. Um, let's try to take an example where AT is cosine t. But before we even take the example, just realize that since x of, just put t equals 0 here, xt equals x0, it must be so, which means phi is 0. So phi is 0 because x0 is, because these two are equal, okay, which means that phi 0 must be 1, and that you can of course see here that the phi t, this fundamental matrix here, it is 1. Now you'll find that in the later systems of equations, which will be the matrix vector system, I mean, you'll find, I mean, there is not a single fundamental matrix. There would be many fundamental matrices, but the one which will be most convenient to use would be the one where phi at time t equals 0 is the identity matrix. But again, that's way down the line. So let's take the example of AT being cos t. In that case, so this is your example, which means that for the example case, xt is x0 e to the power sine t, right? Okay, so as I've mentioned that one of our probably our main goal is to understand time periodic systems, because we want to understand something called the Floquet theory at the end of the day. But and for that, we have to deal with systems where the coefficient is time periodic. What I mean by that is a system exactly like what has been considered like this, right? So at plus capital T, where T is capital T is the period, is A of t. Okay. Now, if that's the case, then let's try to see what the fundamental matrix turns out to be. Okay. So phi of t, just write it in a better way. Phi of t. Okay. Now, you already know what phi of t's definition is. Phi of t is exponential of 0 to t, a t prime, dt prime. So that's the definition. That's phi of t. That's the definition, right? So what is phi of t plus capital T? Is t plus capital T, a t prime, dt prime, right? So let's break it down into two parts. 0 to capital T, a t prime, dt prime. Sorry, my primes are becoming a bit longer. T to t plus capital T, a t prime, dt prime. So should be clear that, oh, sorry, should be clear that this part, this thing here is simply, maybe I should put it here, is phi of capital T, okay? And what is the next guy? What is the next bit? Use some other color. Um, the next bit here, this turns out to be phi of t, small t. And let me prove that. So call this thing as 2 and this thing as 1. So just see what 2 turns out to be. Okay, it is integral of, sorry, um, integral of t to t plus t a t prime dt prime, right? Now, you can simply use a change of variable, right? So the integral, oh, I made a small mistake here. This should be from capital T, right? Because here it is from capital T. So, so you have integrate from 0 to capital T and then capital T to T plus T prime. Okay, right. So let's define I use the method of substitution, right? And if we are using a method of substitution, just use something like call it S equals T prime minus T, right? So which means that T prime is S plus capital T. So this integral becomes a of, so dt prime is simply ds. So t prime is s plus capital T ds, and the limits turns out to be from 0 to t, okay, which means that the integral is from 0 to t as ds, because a of s plus t is a of s by periodicity, the because the function a is t periodic, right? So and the integral from 0 to t as ds is nothing but phi of t, and therefore this is phi of t. So phi of t plus capital T is phi of capital T times phi of small t. Maybe I should name it, number it as number 3. Okay, and uh, um, and this equation 3, you can actually through induction, you can say that phi of is replace t by with t plus capital T. Okay, then phi of t plus 2t equals phi of capital T. The first part is unchanged, phi of t plus capital T. And then again use equation 3 and becomes phi of t times phi of t times phi of small t, which is phi squared t phi t. So you can use by this logic, by this argument, and through induction, you can show that t plus nt is phi to the power n of t times phi of t. Um, Again, I'm just going to box it because it's an important relation. Um, and and just to make sure that we understand this, that you can get equation 3 or 4 only for periodic coefficients. So the equation 2 is generally valid. So equation 2, or call this as um, this particular form, right, is generally valid for any time dependent coefficient. But when you are going into equation 3 or 4, that's only valid for periodic for a periodic coefficient a, where a's periodicity is capital T, right? Now, just to make another point here is noting that phi of at t equals 0, phi 0 is basically 1, which we have already checked here as, where did I go? Here we have already checked that. So which means that phi of nt is phi t to the power n. Okay, so this is also another important corollary of equation 4. So that's all for today. So what we have understood the simple 1D or a scalar system, scalar linear time varying system, and we have seen the problem for the specific case of periodic, when the coefficient a is periodic with a periodicity capital T. So that's all for today. Thanks.